Hello and welcome back to the classroom. My name is Mr. Wong. Today we'll be covering the law of conservation of mass, and hopefully you can get some gauge of in terms of word equations and also, just understanding how the law of conservation of mass works. Okay, so we can quickly revise. The chemical reactions is when a new product is formed from an existing substance. From what we've done so far with chemical equations, we said that we know already that this is H2, H2. So the overall equation we have is 2H2 plus 2 oxygen atoms connected together, and we get H2O and 2 molecules of it. Okay, so that's what we've learned from balancing chemical equations. You can see we have formed new chemicals. You can see from that diagram as well. That's different from, say, boiling water, where we're just spacing out the substances. So there's a difference between chemical and physical change. So a chemical reaction, we said before, the starting ingredients is called the reactants. The end ingredients is called the products. Now, the way we tend to express that is through the arrow. So it's the reactant, arrow across to the products. You could write it the opposite way. So you could write products and then arrow towards, and then write reactants. It really depends on where your arrow is pointing. That's the main point when it comes to reading the equation diagrams. Everything of the product is formed by the atoms of the reactant. So you can't get a new atom out of nowhere. It has to be from your starting ingredients. Now, what dictates this is the law of conservation of mass. Okay. So we previously described chemical equation using word equations. As you can see, different ways we can look at how reactions work. We said that it could be from a production of gas. So if we see any fizzing, it could be, production of light. It could be the production of heat that could demonstrate a chemical reaction. We talked about word equations, right? And that tells us the name of the chemicals we use. We also talked about chemical equations by writing the actual symbols down, like so. And we also talked about how we could balance these chemical equations based on what we can see. So in this case, we have 3 hydrogens. So let's make that a 2. So that's a 2 there, okay? And that's a 2 there, right? So that's kind of what we talked about with that. We also went a little bit more fancy. We even talked about the different type of states that they're in when they react. So that's all pretty good. Then we came across a notion called the law of conservation of mass. So the law of conservation of mass basically states that whatever mass you had at the start of the reaction, that has to equal the total mass at the end of your reaction here. Okay, so not only do I need to have the same type of atoms on both sides, the mass when added up together must equal the same. And it must equal the same so long as it's in a closed system. Okay, so what is a closed system? Let's try and work that out. This is a nice little diagram to show you the difference. We have an open system, closed system, and an isolated system. So the scenario we're looking at here is a closed system this way. Now imagine this is our system. A closed system, the idea is energy can move in and out. So it moves in and out of system. What we mean by the system, it could be the chemical reaction we are creating. Okay. But matter, in this case, anything that has mass, we can think of all the different atoms, compounds, molecules. Those are all forms of matter. Matter cannot move. In an open system, matter can move in and out. So I guess the best analogy for an open system is imagine you are inside a room, but inside the room, the door is open. So at any point in time, you can leave the door. The matter or the mass object can escape. In a closed system, imagine that you're in your classroom and you are sitting down in your chair, and there is no way, or there's no doors, no windows. Not that there will ever be a classroom like that. Therefore, you can't move out of the system. You are stuck inside, right? So the mass object is stuck inside. So that's kind of what we are talking about here with a closed system. Under these kind of conditions, we don't expect mass to change because there's no location or direction for the mass to escape. All right, so let's do a really simple experiment that we can demonstrate the law of conservation of mass. So theoretically speaking, if I have a bit of sodium bicarbonate, or more conventionally baking soda, and by all means you can try this at home if you have the resources. If you have baking soda, you add it with vinegar and you put it in a structure like this. So you have sort of a little glassware, and then you have something covering the glassware to mix it up. You get a nice little chemical reaction occurring here. What you should find is the total mass. So this value here, in this case before, was about 243.68 grams. The mass after is still exactly the same. Okay, so that's that's how we can prove the law of conservation of mass. If you've done a chemical reaction, the mass hasn't changed, you've obeyed the law of conservation of mass. Now, what you can see here, if you actually think about, so what does the balloon actually do in this scenario? Well, the balloon, theoretically speaking, is trying to create a little seal to block the atoms escaping, or block the atoms from leaving the system and going into the surroundings. So our surrounding in this case is anything outside of the volumetric flask and the balloon. Anything inside the flask, that is the system. This is where the chemical reaction is occurring. Okay, so our system is where the chemical reaction is. That's what we have here. So how can you set this up at home? Very simple. You just need a bit of glassware. You just need a bit of vinegar. And so long as you can create an airtight seal of some kind over your glassware, you can test out this experiment for, law of conservation of energy. So in terms of the equipment you need sodium bicarbonate. This is effectively baking soda. So most people should have this. And then you have acetic acid, which is just vinegar. Again, you should have this at home. What you need to do is put the powder or the baking soda powder into the balloon, okay? Seal it over your glassware. In the bottom of your glassware, you have your vinegar. That's the idea. Now, just change color. Once you've made the seal, then flip your balloon over so that it's sort of standing, so vertically standing like so, and all that baking soda goes to the bottom of the vinegar. As soon as that happens, you will get an immediate reaction. You will get a lot of bubbles fizzing, and bubbles are formed because of the production of carbon dioxide gas. Okay? What you should also find that is in this reaction, it is an example of an endothermic reaction, which we'll talk a little bit more later on in other lessons. And what actually happens is the surroundings will become cold. So when you touch the piece of glass, you'll find that it becomes cold. Now the reason for that is because in this reaction, energy from the surrounding in the form of heat is being absorbed to allow this reaction to occur. You'll get sodium acetate, so a type of salt, and then you get water in it as well. So that's how you perform this experiment here. So when I did this experiment in my own lab, these were the statistics that I found. So the mass of the acid and the balloon was 32 grams, and then I recorded my own mass of the calcium carbonate. So originally, before the reaction occurred, my total mass was 33.01 grams. Okay. Now after the reaction, I got 33.00 grams. Okay. So there is a slight loss of mass. So I actually lost 0.01 grams in the process. Now the question is, I guess, where did that 0.01 gram disappear to? Because according to my results, it didn't obey the law of conservation of energy. Okay, so the question we need to consider is, why didn't it obey it? Now, when it comes to a scientific law, it should be something that can always be observed. So if I can't observe it, have I violated the law of conservation of energy? Well, not quite. A potential reason why, if you perform this experiment with a balloon, the reason why it doesn't occur, or why you can't see the exact mass, is a thing called permeability. So inside a plastic, or inside the balloon, let's say, on surface value, we see it as everything is really tightly sealed on the surface of the balloon. But that's actually not what's actually occurring. In some plastics, like the balloon, they have really, really tiny holes in between. So really, really tiny gaps in between, but not tiny enough that it doesn't allow for the carbon dioxide gas to escape the membrane of the plastic. So the reason why I could be losing mass is because the membrane of the plastic the gaps between it isn't small enough. What we call is semi-permeable, and that actually allows for the carbon dioxide gas to escape. Okay, what could also occur potentially is the electronic balance. If I didn't scale it properly, that could also affect the results. Or it could just be, besides the fact the balloon is only semi-permeable, it could also have just been that I didn't seal it completely. So that could have been one or two of the reasons. But this should still follow the law of conservation of mass regardless, because even if some of the mass did escape my system, so let's say the CO2 escaped, overall speaking, I should see within some confined area of space, some closed system, I should still see that I've had the same mass regardless. So that could be a potential that you can look into there. Regardless, though, the overall change is quite small. So the overall, the overall change we see is very small. So that would demonstrate the law of conservation of mass was mostly obeyed, barring perhaps a little bit of a defect in the balloon, or maybe it was semi-permeable regardless. Okay, so hopefully this explains to you what the law of conservation of mass is, what kind of conditions will allow for the conservation of mass to occur. It needs to be a closed system. And so, yeah, hopefully that makes more sense. So we could say the system was not perfectly closed. Right, my name is Mr. Wong. Thank you for joining me today. Hopefully this video was of help to you in explaining the law of conservation of mass. There are some other videos you can look into, but until we have our next lesson, have a good day and enjoy.